In this video lecture, I'm going to introduce the concept of Lewis structures. Lewis structures are a way of looking at a covalent molecule and determining the way the electrons are distributed between the atoms in that molecule. So we know that a covalent bond forms when electrons are shared between atoms. A Lewis structure represents electrons as dots and bonds as dashes. And it's a technique that lets us figure out the way those electrons and bonds have to be distributed around the atoms. Lewis structures are the first step to understanding the geometry of a molecule, which will be the next topic we tackle. So some basics you need to know about Lewis structures are that we use a dot to represent electrons and a dash to represent a bond that is two shared electrons. The definition of a Lewis structure is a representation of covalent bonds in a molecule. A representation of covalent bonds and electrons in a molecule. You can also do Lewis structures for just an atom, but that really doesn't tell us much. When we do a Lewis structure, we are focusing specifically on the valence electrons and the way they're interacting with each other. So we focus on valence electrons and the way they interact. Valence electrons are something we learned about in the last section on electron configurations. They are the electrons in the outermost energy level, that outermost shell of electrons that generally corresponds to the row of the periodic table. So if we were to make a Lewis representation of just an atom, it would be fairly simple. We would represent the valence electrons with a dot. So we would put the valence electrons as dots around the element symbol. So for example, hydrogen, its symbol is H and it has one valence electron. Carbon, its symbol is C and it has 4 valence electrons. Fluorine, its symbol is F and it has 7 valence electrons. All right, in case you're wondering where I'm getting these 1, 4, and 7 from, let's take a look at how I'm counting those up on the periodic table. So for example, for fluorine, I said there were 7 electrons. Fluorine's valence shell is here in the n equals 2 level. And so we would count across 1, 2, 3, 4, 5, 6, 7. That's where I get the 7 electrons for fluorine. So again, these are the valence electrons, not the total electrons, just the ones that are in the outer shell. We could also look at carbon here. I said carbon had 4. Carbon is here on the periodic table, also in n equals 2, and it has 1, 2, 3, 4 valence electrons. Okay, so as I said before, The Lewis symbol for an element by itself really isn't that interesting. All it tells us is how many valence electrons there are. But if you can do a Lewis representation for an element, then you're beginning to understand the way that these would combine to make a molecule structure. So let's start looking at that on the next page. I'm going to start with the molecule F2. Since we just looked at the structure for fluorine, it should be sort of fresh. So fluorine has 7 valence electrons. And if I draw it like this, so that each side has 1 electron on it, then we could see how these 2 electrons might be shared to make a single bond, which we would represent with a dash. The Lewis structure then for the molecule would be this, where we replace those 2 single dots with a dash that represents that 2 electrons, 1 single dash, represents that 2 electrons are being shared between the 2 fluorine atoms. So why would fluorine want to share its 2 electrons? The reason behind this is something known as the octet rule. So it's called the octet rule, where oct stands for 8, although I like to refer to it as the noble gas rule. And the octet rule, or the noble gas rule, says that atoms want to feel like they have a full subshell, or a full shell of electrons. Atoms want to feel like they have a full shell of electrons. Now, obviously, that's not the official definition, that's the Seton definition, but I think it helps. We already know that atoms want to gain or lose electrons to be like a noble gas when they form ions, so it should make sense that when they form covalent compounds, they also want to be like a noble gas. Well, it turns out that the noble gases have 2 electrons in an s orbital, and 6 electrons in a p orbital. And so together 2 and 6 make 8, and that's where we get the octet rule from. So generally speaking, when we make Lewis structures, we're going to look for each atom in the structure to feel like it has 8 electrons. I use this word feel like they have electrons because in a covalent bond, the electrons are shared. So they don't actually have 8 whole electrons. They just feel like they have 8 electrons. For example, if we look up here at fluorine, each fluorine has 6 valence electrons and then 1 single bond. We say that this single bond sort of belongs to both of them. So this fluorine feels like it has 8 electrons, and this fluorine feels like it has 8 electrons. Even though technically between the both of them, they're short 2 electrons to actually both have 8 electrons. But that sharing allows them to feel like they have the electrons. The reason I prefer to say it's the noble gas rule instead of the octet rule is that not all noble gases actually have those 8 electrons. In fact, in reality, only neon does. Helium only has 2 electrons. Neon has 8 electrons. And then when you get lower than neon on the periodic table, there are d orbitals available. So argon, krypton, xenon, they all can actually have more than 8 electrons because of those d orbitals. Often they still have 8, but they can have more. So because of the d orbitals that are there, argon and the noble gases below it, krypton, xenon, and radon, can all feel like they have more than 8 electrons. Since you can have situations like helium or argon, krypton, etc., that have more than 8 electrons, I feel like the octet rule is, the name is just really misleading, and that's why I like to call it the noble gas rule. But what you're going to see in the literature, in your textbook, if you're YouTubing videos, etc., is the octet rule. All right, so let's look at another example of how we can get atoms to share electrons so they feel like they have their 8 electrons, or they feel like they have a complete octet. And we're going to do this with a really common molecule, water. So hydrogen has 1 electron. Oxygen has 6 valence electrons. And there are 2 hydrogens. Hydrogen's nearest noble gas is helium. So we could say hydrogen wants to be helium, and oxygen's nearest noble gas is neon. So helium only has 2 electrons in its full shell. Neon has 8 electrons. So we're going to want to share electrons here so that the hydrogen both hydrogens feel like they have 2 electrons, and the oxygen feels like it has 8 electrons. So if we make single bonds here using the 1 electron on the oxygen and the 1 electron on the hydrogen, then now this hydrogen feels like it has 2 electrons. This hydrogen feels like it has 2 electrons. They're both in that covalent bond. And then oxygen feels like it has 8 electrons. 2, 4, 6, 8. So again, we count those shared electrons towards the total electron count of both atoms in the bond. Let's do one more example here. We're going to do the molecule O2. Again, oxygen has 6 electrons. And you may notice that I sort of move around the way I display those electrons. That's fine. It really doesn't matter where you put them around the atom, as long as you have the right number of them. I find it helps to kind of think of them as a box, 2 on the top, 2 on the bottom, and 2 on each side. But they don't have to be that perfectly symmetrical. Okay, so O2 is a molecule. Each oxygen has 6 electrons, so it needs 2 more. In order to get us 2 more electrons, we're going to have to make 2 bonds, so that the structure of O2, if we sort of balance it out better, would look something like this. In this structure, each oxygen feels like it has 8 electrons. 2, 4, 6, 8. 2, 4, 6, 8. So what we're seeing here is that you can have more than one type of bond. Before I move on and go through what I call my 7-step strategy to Lewis structures, I want to talk about the different bond types that are available. So you can have a single bond, which is 2 electrons shared between 2 atoms. You can have a double bond, which is 4 electrons shared between 2 atoms. And you can have a triple bond, which is 6 electrons shared between 2 atoms. As you go from a single bond to a double bond to a triple bond, the bonds get stronger and they also get shorter, so the bond lengths decrease. Single bonds are the longest, triple bonds are the shortest. So they get stronger that way, but longer this way. So that triple bonds are the shortest and the strongest. Triple bonds are the shortest and the strongest. And single bonds are the longest and the weakest. Before we can start making Lewis structures, I need to touch on one other topic, and that's the concept of electronegativity, which is given the Greek letter chi as an abbreviation. Electronegativity is how it's an atom's ability to draw electron density into itself in a bond. An atom's ability to draw electron density into itself in a bond. So the more electronegative an atom is, the more it pulls electrons in, the more it wants electrons. The less electronegative an atom is, the less it pulls in those electrons, the less it wants it. Electronegativity is measured on what we call the Pauling scale. There are other scales, but the Pauling scale is the most common, and it's sort of like GPA. It ranges from 0 to 4.0, although nothing has an electronegativity of 0. So really our lowest electronegativities are going to be about 0.7 or 0.8 to 4.0. This electronegativity value is on your periodic table. The periodic tables that I said we would be using all semester, those bright orange ones that you have. On the box on your periodic table in the corner here, there's going to be a number that's somewhere between around 0.7, 0.8, or 4.0. That is the electronegativity number. So you may notice that fluorine has an electronegativity of 4.0. It is the most electronegative atom. So everything else has an electronegativity of less than 4. Oxygen, which is right next door, and chlorine, which is right below, both have 3.5. And that's a pretty high electronegativity value. So those elements are also pretty electronegative. I'm sorry, I misspoke there. It's oxygen has the electronegativity of 3.5, which is the second highest. Chlorine's is high, but not quite that high. All right, so electronegativity isn't something you need to memorize or anything. You'll always have that periodic table available. I just needed to address what it was because one of the concepts we're going to see next in how we make Lewis structures is that the least electronegative atom will be in the middle. Then a little bit later, we're going to learn about polarity, and electronegativity will play a role in that. All right, let's finally start to put this all together and make some Lewis structures. This 7-step guideline for making Lewis structures is on Canvas. It's called the Lewis Structures Guide. I'm going to go through it and do this for an example of the polyatomic anion carbonate ion. So the 7 steps shown here are what I recommend you do when you make a Lewis structure. Sometimes in high school chemistry and other courses, you learn about making Lewis structures by sort of pushing around electrons and making dashes until it seems like everything has an octet or the appropriate number for its level. This will work, but it definitely has limitations and won't always get you the right answer, especially when you have atoms that are lower on the periodic table and can have more than 8 electrons in it. So I highly recommend you kind of just dismiss from your mind any other way of making Lewis structures you've ever learned and give this one a chance. It's a little bit tedious at first until you get the hang of it, and then you can make them more quickly. So I know that it's going to seem like a lot, but I promise learning to do it this way is really, really worth it. So when we make Lewis structures in this method, what we're going to be thinking about is this idea that it's a very communal idea. It's an idea that each atom brings its valence electrons to the dinner party of valence electrons, and that's their contribution. So you can think of there being like a bowl of electrons around this table, and each atom is sort of putting their valence electrons into the bowl, and then they're going to spread them out and share them so that everyone has enough. The reality is that this is really what actually happens in molecules. When atoms combine and form molecules, they move their electrons from atomic orbitals to molecular orbitals. So the atoms no longer, or the electrons no longer belong to those sort of individual atoms. They belong to the molecule as a shared grouping. Okay. So the first step to making a Lewis structure is to put all of our electrons in the pot by adding up the valence electrons for each atom. So we're going to do this here. Carbon has 4 electrons. Oxygen has 6 valence electrons, and we have 3 of them. So that gives us 18 electrons. And then because this is a polyatomic ion, it's charged, we're going to add electrons to account for that 2 minus charge. So that's going to give us 2 extra electrons. If this was a polyatomic cation, we would subtract the electrons. Because it's an anion, we added the electrons. So now our electron bowl is going to contain 24 electrons. And we have completed step 1. Step 2 is to draw a skeletal structure of the molecule. The skeletal structure is basically like what is the bare minimum we need to have this molecule held together. When we do this, we put the least electronegative atom in the center. So carbon has an electronegativity of 2.5, and oxygen has an electronegativity of 3.5. So clearly oxygen is the lower electronegativity, and that's going to be in the center. So carbon is going to be in the center. And in order for there to be 3 oxygens, we need a minimum of at least one single bond to each oxygen. So this would be the skeletal structure. It's the bare minimum that would represent how these atoms connect together. So that is step 2, done. Step 3, for each single bond, subtract 2 electrons from the available electron count. So a single bond, as we learned earlier in this video, is made up of 2 electrons. In order to make these 3 single bonds, we needed to use 6 electrons from our bowl. That brings us down to 18 electrons. So that's step 3, done. Step 4 is to complete the octet of the outer atoms by adding lone pairs. I'm sorry, there's a typo in this. This should say the outer atoms, not outer electrons. Complete the octet of the outer atoms by adding lone pairs until all octets are complete, or we've used up all the electrons, whichever one comes first. So right now, as it's drawn, each oxygen feels like it has 2 electrons. We've put the single bond in, and remember it started with 6 electrons, but we put them in the pot, so essentially it had no electrons, no valence electrons anyway, and now we've given it a single bond, so it feels like it has 2 electrons. So to complete its octet, we need to add 6 more electrons to it. So now this oxygen feels like it has 8 electrons. 2 in the bond and 6 in the single electrons. We call them lone pairs. It just means that pairs because they typically come in 2, and lone means they're not in a bond. So we call these electrons that we added lone pairs. So that used 6. I still have 12 electrons remaining, so I'll put 6 more on this oxygen and 6 more on this oxygen. That used up all 18 electrons that I had, and it also completed the octet of the outer atoms. So we'll check number 4. Every time you add electrons either into a bond or on as a lone pair, you should adjust your electron count like I'm doing here on the side. Step 5, if any electrons are left after number 4, we put them on the center atom. Well, we don't have any electrons left, so that step is already done. Step 6, if the central atom has an incomplete octet after number 5, move 1 or more electron pairs from an outer atom to make a multiple bond until all atoms have a complete octet. Okay, so does our carbon have a complete octet? It has 2 for this bond, 2 for this bond, and 2 for this bond. That's only 6 electrons. It needs 2 more. So what we're going to do to get more is from one of these oxygens, we're going to make a double bond. So now it's going to look something like this. And so now carbon feels like it has 8 electrons in the 4 single bonds. The outer oxygens, this one and this one, also both feel like they have 8 electrons, just like they did before. And this oxygen that we moved the electron pair in also still feels like it has 8 electrons. 2, 4, 6, 8. So even though now those electrons are in a bond instead of directly on the atom, they're still contributing 2 electrons to oxygen. So you might be asking yourself, well, why did I take it from that oxygen? Why not this one or this one? And the reality is it could have come from any of those, and it does come from any of those. What that is resonance structures, and that is our last step here. So we just did number 6. We moved the electrons into a multiple bond. until we had a complete octet for everything. Now we can draw resonance structures, which is step 7. So this would account for the fact that when you make a double bond, it could have come from any of these carbon atoms. I'm sorry, any of these oxygen atoms. And so we will draw all of them with double-sided arrows in between them. So I flipped my oxygen from the top to the bottom just because I was getting close to the bottom of the page here. But what I want you to see is that in these 3 structures, they're sort of the same, except that whichever oxygen has the double bond moves. And so the reality is that electrons move, right? We learned that electrons are in an electron cloud moving rapidly around the outside of the nucleus. When you make a molecule, electrons are still rapidly moving around. It's just now instead of around one nucleus, they're moving around the whole molecule. So at any given point in time, the molecule may have its electrons distributed in any of these 3 ways. It's moving back and forth between all of them. And so that's why we put the double-sided arrows in between to recognize that the structure is resonating between all 3 of these. All right, last of all, this is an ion, right? It had a 2- charge. So because it was charged, we're going to put a bracket around the whole thing and indicate what the charge was. We only have to do that last step, the bracket, and the charge for when we're doing it for an ion. If we're doing it for a neutral molecule, you can skip that part. Okay, let's do just a couple more examples of some Lewis structures. And I'm going to start with a really simple molecule and sort of work our way up to sort of more complex ways so you can see how we do these for different situations. We're going to start with water because it's simple. And we already know what its Lewis structure is supposed to look like, so this will let us see how we get to the same structure following the steps. So I said that you always put the least electronegative atom in the center unless you're dealing with hydrogen. Because hydrogen can only have 2 electrons, it's always on the outside. So we know that oxygen is going to be on the inside. So first we have to count up our available electrons. There's 6 electrons for hydrogen or oxygen and 1 electron for each water. That gives us a total of 8 electrons. Our skeletal structure is a bare minimum of a single bond between each hydrogen, making those 2 single bonds used 4 electrons. That leaves us with 4 more. Hydrogen's octets are full. Hydrogen can only have 2 electrons max because it's like helium, so that's done. Oxygen is not full, but even if it wasn't, so we're moving on from step 4 to step 5 at this point in time. So step 5 says if there's any electrons remaining after the outer atoms have their octets complete, we put them on the center atom. So that means these 4 electrons go on the center atom. If anything has an incomplete octet at this point in time, we would move things around to make multiple bonds, but it doesn't. Everything's good. Hydrogens need 2, oxygens need 8. They have what they need. So this is it. That's the Lewis structure of water, and that's how we get it following our steps. Okay, let's try something a little bit outside of the box. Xenon F2. So we always think of noble gases as being unreactive. They don't make compounds, but they will with other really, really reactive elements. So fluorine, because it's so electronegative, is really reactive. So we can make this molecule using a noble gas. All right, so our available electrons, xenon has 8 electrons, Each fluorine has 7 electrons. That gives us a total of 22 electrons to work with. Xenon has lower electronegativity, so it's going to be in the center when we make our skeletal structure. We needed 2 single bonds, so that used 4 electrons, which leaves us with 18 electrons. Each fluorine needs 6 more to complete its octet. That used 12 more electrons, leaving us with 6. That was step 4. Step 5, put any remaining electrons on the center atom. I have 6 electrons remaining. I'm going to have to put 6 electrons on the center atom. If I needed to at this point in time, I could make double bonds, but obviously I don't need to because everything has 8 or more electrons. And so you might think, well, this is impossible. Xenon is violating the octet rule. It has 2, 4, 6, 8, 10 electrons. You're only allowed to have 8. What happened here? Well, remember I said that elements lower than neon on the periodic table have d orbitals. Xenon has empty d orbitals that can hold extra electrons. So if an atom is in n equals 3 or lower, it can have more than 8 electrons. So this is okay. And the structure I have drawn there is indeed the structure of xenon difluoride. All right, we're going to do one last example here, and we're going to do it for NCS minus, the thiocyanate ion. This will give us a little bit more practice with what to do when we have a charge, and it will also give us a little bit more practice with resonance structures. So nitrogen has 5 valence electrons, carbon has 4 valence electrons, and sulfur has 6 valence electrons. Plus we have a negative charge, so that will give us 1 more electron, which brings our total to 16 electrons. For electronegativity, carbon is the least electronegative. It's going to be in the center, and we'll have a single bond to each of the other 2 atoms, which used up 4 electrons, leaving us with 12. We need to complete the outer octets. Each one of these needs 6 more electrons. That used up our remaining electrons. The outer atoms, their octets are happy, but our center atom, carbon, only has 4 electrons. So we're going to need to move some of these electrons into double bonds. So one option is to move 1 pair of electrons from nitrogen and sulfur. Another option we could have done is to move 2 from one of them. Or 2 from the other one of them. All of these are perfectly reasonable options for completing the octet of carbon by moving into these bonds. So these would be resonance structures with each other. So the total Lewis structure would be the combination of all 3 of these resonance structures. Because it's an ion, we would add the bracket and the charge. All right, so those are some examples of how we make Lewis structures. What I'd like you to do now is open on Canvas the Lewis structure handout that you have, the worksheet, and there's like 3 pages of molecules for you to try making Lewis structures of. I also put naming on there just to kind of throw in a little practice for us on naming because we haven't done a whole lot with that this semester. But that's sort of a side topic. Really, I want you focusing on making the Lewis structures using this 7-step method. I will be posting an answer key for that.